All right, so let's talk about electron configuration and electron filling. So as we said before, what we're going to do is we're going to put electrons in these orbitals, right? Put these electrons in their little houses. And as might be expected, electrons are going to fill from lowest energy to highest energy. So electrons fill lowest and available energy orbital. This is called the Aufbau principle. You don't have to know the name, you just have to understand the idea. Electrons fill from low energy to high energy. So let's think about our energy and our quantum numbers and what they mean. So our most important quantum number is n. Remember, we said n was the principal quantum number, which determines the overall size and energy of the orbital. So as n increases, think about what happens to energy. And the correct answer is energy increases, right? So as n goes up, energy goes up. So if we're thinking about the order of filling here, we're going to go start off at n equals 1. Remember, n cannot equal 0. Then we're going to go to n equals 2. Then n equals 3, right? So we're going to go from left to right, higher and higher numbers. Now remember, n is the principal quantum number, but in any n, there's subshells. There's different values of L's, right? N is the overall energy and the size of the orbital. L is the shape and somewhat the energy as well. So let's take a look at what happens as L increases. So as L increases, energy also increases, right? So it makes sense. As the number gets bigger, you get more energy. So if we're thinking about L here, when it goes first, lowest energy would be 0, then 1, then 2, then 3. But remember, we don't talk about L in terms of these numbers. We use the letter designation. So again, for L equaling 0, it's S. L equal 1 is P. L equals 2 is D. And then L equals 3 is F, right? So we're going to go from left to right, higher and higher energy. Then we have our final, or not our final quantum number, but the final quantum number that describes an orbital, and that's m sub L. Remember, m sub L is just the orientation of the orbital. So, whether it's pointing up and down, left and right, in and out of the board type of thing. And so since it's just the orientation, it doesn't actually cause any energy differences in the orbitals. So if you have the same n and you have the same L, even if you have different m sub L's, your energy levels are the same. And so what we say when energy levels are exactly the same, we say that they are degenerate. So degenerate means same energy. So we have different m sub L orbitals are degenerate. So if we're thinking about energy here, and we're thinking about maybe let's take a look at a 2p orbital, right? Remember, p orbitals, there's 3 of them. So m sub L can be -1, 0, and 1. And you can see that they're all the same energy level, right? They're degenerate. Some other things you have to keep in mind is that there's only 2 electrons per orbital. So if you're thinking of these kind of orbitals as little houses, there's only 2 electrons per house, right? And remember, one of these electrons is going to be spin up, one is going to be spin down. So spin up, we draw this half hook arrow pointing up. And then spin down, we draw this half hook arrow pointing down. And remember, the spin up and spin down are the quantum numbers m sub s. So when you're pointing up, you're +1/2. When you're pointing down, you're -1/2. And because of this, because the electron, you can only fit 2 per orbital, one spin up, one spin down, what ends up happening is that no 2 electrons can have the exact same 4 quantum numbers. And we'll explore this more later on. This is known as the Pauli exclusion principle. Again, you don't have to know the name, you just have to know how to apply it. And so if we think back to this diagram that we saw earlier, this is the rules above are just describing this diagram. So you can see we have energy right here. So we're going to fill from the bottom, right? So we're going to put one electron there. One's going to be spin up. And then when we put another electron, it's going to go there. Now this orbital is filled, so we can't put any more up. So we got to go to the next highest, and so on and so forth. And we'll discuss kind of how to fill these in greater detail coming up. And so, right, you don't have to memorize this diagram. Next up, we're going to show you how the periodic table can be used to get all of this info very simply. Right, so the periodic table has all of this information in a very simple way to read it.